And we come to our next talk, which again will be a more lattice-orientated talk by Zhang from the Central China University in Wuhan. And he will talk about Dirac eigenvalues in their correlation and their role for the axial anomaly. So you please go ahead.
Okay, thank you. Hello everyone, I'm Zhang from CCNU. Firstly, I would like to thank the organizers for giving me the opportunity to present my very recent work based on this paper. Today, I would like to talk about the correlated Dirac eigenvalues and the axial anomaly in the symmetric QCD. And those are my collaborators. This is the outline of my talk. I will start with the motivation and then talk about the UA1 symmetry and the relation between the mass derivative of the eigenvalue spectrum with respect to the quark mass and the n+1 point correlation functions. And then introduce our lattice setup and then show you our results. And finally, I will summarize my talk. Let's move on to the motivation. At a temperature larger than the critical temperature, we know that the symmetry is restored. And how about the fate of the UA1 symmetry? The UA1 symmetry could affect the order of the phase transition with two massless light quark flavors at a temperature larger than the critical temperature. If the UA1 symmetry is broken, then in the limit, the order of phase transition is second order, and it belongs to the O4 universality class. If it is effectively restored, then the order of phase transition could be either first order or second order. However, there is still no consensus with the lattice community on whether the UA1 symmetry is effectively restored or badly broken due to the lack of the continuum and the extrapolation. And what observables should we look at to investigate the UA1 symmetry? Well, we can look at the two-point correlation function of the scalar and the pseudo-scalar. Its integrated function susceptibility kappa minus chi delta is defined as follows. If it is 0, then we see that the UA1 symmetry is restored. At a temperature larger than the critical temperature, due to the degeneracy of pion and the sigma meson, so in the limit, kappa minus chi delta is equal to the chi disk. So the chi disk can also be used to signal the restoration of the UA1 symmetry. And to deeper look into its microscopic origin, it can be related to the Dirac eigenvalue spectrum. The condensate of the parameter of the symmetry can be related with the eigenvalue spectrum as follows. In the limit, it reaches to the Banks-Kisher relation parallel 0. The UA1 measures kappa minus chi delta can be described by the eigenvalue spectrum like following. From the denominator, we can see that it is very sensitive to the small eigenvalues. So if there is a gap in the near zero mode, then we can see that the UA1 symmetry is effectively restored. Another UA1 measure chi disk is related with the first derivative rho with respect to the quark mass. So to understand the underlying mechanism of the axial anomaly, we also propose to look into the mass derivative of the eigenvalue spectrum. And the weakly interacting instant gas motivated eigenvalue spectrum is proportional to the m squared delta lambda. It can lead to the manifestation of the axial anomaly even in the Cal limit. The m squared factor is coming from the two fermion determinant. The delta-like structure is motivated from the small shift of the zero from the near-zero modes can be neglected. In a recent review, the lattice QCD studies show that at a high temperature for the physical light quark mass, the temperature dependence of the UA1 measure topological accessibility follows the dilute incident gas approximation prediction. Whether these findings is due to the underlying mechanism of rho is proportional to the m squared delta lambda, and what happens for the m goes to 0 is unanswered. Some lattice QCD studies have observed this infrared enhancement as shown in the red plot. Using it is the partially quenched scenario overlap on HISC, while some other lattice studies have not observed this infrared enhancement as shown in the left plot on the unitary scenario overlap on overlap. Whether this infrared enhancement is due to the partially quenched effects needs to be investigated, and the underlying mechanism is not clear. And we looking into the mass dependence of rho. From the plot, you can see that the mass dependence can be hardly observed from the rho directly. So we propose and introduce the derivative eigenvalue spectrum with respect to the quark mass and the correlation among the eigenvalues. For the 2+1 flavor QCD, the eigenvalue spectrum is defined as following. The rho u is written in the right-hand side. Lambda j is the eigenvalue of the massless Dirac matrix on a given SU3 gauge field. Here we should note that the rho u itself does not explicitly depend on the quark mass. The mass dependence enters rho through the integration over the gauge field. From the definition of rho, we can easily derive the first derivative of rho with respect to the mass and the second derivative rho with respect to the mass square, and so on and so forth. And it is related with the correlation, endpoint correlation among the eigenvalues, which is defined in equation 3. And before going to our lattice setup, let me emphasize our purpose one more time. In this talk, we want to show you two things. First one is how axial anomaly manifests itself in the chi-mass chi-delta and the chi-disk at a temperature around 1.6 times the critical temperature, and if it is manifested, then what is the underlying mechanism of it? And then let's see our lattice setup. Our simulations are performed on the 2+1 flavor QCD using the highly improved staggered quark and tree-level semantic gauge action at a temperature around 105 MeV, which is correspond to 1.6 times the critical temperature. The strange quark mass is fixed to its physical value, and we used 5 different light quark mass, which corresponded to the pion mass from the 55 MeV to the 160 MeV, which can allow us to really do the chiral extrapolation. We also have 3 different n-tau, 8, 12, and 16, which can allow us to do the continuum extrapolation, and also have several volumes to investigate the volume effect. And here is our continuum and the chiral extrapolated results for the chi pi minus chi delta and chi disk from the direct measurement of the inverse of the fermion matrix. First, let's look at the left plot, chi pi minus chi delta. For the consistency check here, we did 2 extrapolations corresponding to these 2 different bands. Blue band represents the joint extrapolation, and this magenta band means first do the continuum extrapolation and then do the chiral extrapolation. And the same procedures followed for the chi disk. From these 2 plots, we can see that after continuum and the chiral extrapolation, the chi pi minus chi delta is equal to the chi disk, which is expected in the chiral symmetric phase, and it is non-zero, means that the actual anomaly remains manifested even in the chiral limit at a temperature around 1.6 times the critical temperature. And then I showed you a comparison of these 2 quantities, chiral condensate and chi2, from 2 different measurements. One is from the direct measurement of the inverse of the fermion matrix. The other is restricted from the rho and the second derivative rho with respect to the mass square. From these 2 plots, these 2 different measurements corresponded to this open and filled symbol. From these 2 plots, we can see that the chiral condensate and chi2 can be reproduced very well from the rho and the second derivative rho with respect to the mass square. And the dashed line in the left plot denotes the linear fit in the quark mass to the directly measured chiral condensate. As you can see from the plot, for all 3 lattice basins, the chiral condensate vanishes in the chiral limit, which is expected in the chiral symmetric phase. And then we showed you the comparison of 2 U1 measures, chi pi minus chi delta and chi disk, obtained from the 2 different measurements. And we show the results for all the n-tau and all the quark mass. You can see that the rho and the first derivative rho with respect to the mass successfully reproduced the directly measured chi pi minus chi delta and chi disk. We also observed that only infrared part of rho and the first derivative rho with respect to the mass are needed for the reproduction. And also we can see that both these 2 UA1 measures are linear in the quark mass square, at pion mass below than the 140 MeV. And the consistent results of those quantities from two measurements make us confident to extract the information on rho and its mass derivatives. And then let's look at this derivative of rho with respect to the mass look like. First, I showed you the quark mass dependence of the first derivative of rho with respect to the quark mass divided by mass, which is shown in the plot, the open symbol, and the second derivative of rho with respect to the mass square, which is a field symbol in the plot, at a fixed n tau 8. From the plot, we can see that these two quantities are almost consistent with each other, and it is almost independent of the quark mass. We also observed a peaked structure developed at the small lambda range, and it rapidly dropped to zero as lambda increases. And then let's look at the lattice spacing and the volume dependence of the second derivative of rho with respect to the mass square, and also the third derivative of rho with respect to the mass cubic. We can see that the second derivative of rho with respect to the mass square in the small lambda range becomes sharper as we go to the continuum limit. And we also observed that the third derivative of rho with respect to the mass cubic close to zero within errors. And also you can see that the volume dependence is quite small. And the consistency of these two quantities shown in the left plot, together with the third derivative of rho with respect to the mass cubic close to zero, lead us to conclude that in the small lambda range, in the Q limit, the eigenvalue spectrum is behave as the M square behavior. And we also look into the differences of the mass derivatives with its Poisson distribution. From the plot, we can see that this positive non-Poisson correlation with the small lambda range give rise to the peak developed in the small lambda range of the Dirac eigenvalue spectrum. With this, I would like to summarize my talk. Firstly, we showed that the actual anomaly remains manifested in the chi-pi mass chi-delta and the chi-disk, even in the Q limit at a temperature around 1.6 times the critical temperature. And then we found that the peaked structure developed in the small, and we also found that this peaked structure developed in the small lambda range is due to the non-Poisson correlation with the small eigenvalues. And this peak becomes sharper as we go to the continuum limit, and its amplitude is proportional to the M square. And this suggests that at a temperature larger than the 1.6 times the critical temperature, the microscopic origin of the actual anomaly is driven by the weakly interacting instanton gas motivated in the small lambda range, and in the Q limit, the eigenvalue spectrum will behave as the M square. Delta lambda, sorry, there is a typo. and the Kelfis transition in the 2+1 flavor QCD is a 3-dimensional all-4 universality class. So that's all. Thank you.
Yeah, thank you very much for this interesting talk on new observables. So we have still some time for questions, and I see a hand raised by Haitao Shu.
Yes, thanks for your nice. So you should pi minus chi delta, which is one of the U1A measurements. I'm wondering if you ever look at the chi 8 minus chi sigma, because I mean it's also one of these U1A measurements.
Chi8 minus chi
Yeah.
sigma. Oh, we didn't look into this observable. We didn't calculate.